Okay, so we learned to find mean and max. They're very, very important operations in the sequence. By the way, just simple question. Well, Preet, you could move it wherever you want. You are the next victim. Okay. So how many comparisons do we need to find a mean of 5 elements? Max? Why? Why couldn't we do it with 3?
If you already know the menu, you can. If you already know the menu, you can.
Yes, if you already know, then you don't need any, yes. But if you don't, why do we need n minus 1 comparisons? What do you think?
If you don't want to compare the same item to itself.
We need n, but maybe we could do it with n minus 2. Why couldn't we do it with n minus 2 comparisons? Maybe there's a clever algorithm.
Compare with all the elements.
Could we do it with n minus 2 or not? Why not? Do we have an argument? Anyone?
When you don't compare, you don't know.
That's random, so you have to compare every single one.
One comparison reduces number of elements by 1.
Okay, the simple argument, this is correct, but the simple argument to remember is that n minus 1 guys have to lose. Right? We're finding a winner in our competition. Right? If a person didn't play in a competition, if he didn't lose, we cannot eliminate him. And we need to eliminate all but 1. Right? So we will, the reason I give this form, because we'll soon dwell on it. Now, so we need n minus 1, yes?
One of the parts of the proof, which is we need a connected tree, so.
You need a connected tree, yes, yes. But also we need to, every person but 1 needs to lose a match.
But that just means you need n by 2 matches.
No, it doesn't mean it at all. N by 2 matches, only n by 2 will lose.
Oh, all of them need to lose, right? Okay, yes, yes.
We will do it very soon now. Okay, so now how many do you need if you want to find minimum and maximum?
Together?
Yeah, together. Because sometimes you want to estimate, you want to say what my min, what my max. Well, obviously we could do it with 2n minus 2. Yes. But do we need 2n minus 2?
3n by 2.
Very good. How do we do it? Let him talk. We'll implement you and I.
We first take the first 2 elements and find the min and the max. Then take the remaining 2 in pairs and do one comparison to find the minimum and max of those 2. And compare the min with our current minimum and max with the...
Very good. Very good. This is the algorithm which was invented by Ira Pohl of UC Santa Cruz in, believe it or not, mid-70s. Nobody figured it out till then. So, and the idea is, let me repeat, we will work on the code right now, is very, very simple. The idea is that let us assume that somehow we worked up to the middle of our list, of our range. And we have a running min and running max. The temptation is take new element, the next element, compare him with min and with max. That's very sad, because very often we will do 2 comparisons and then discount it. Right? So for 1 element, we'll be doing 2 comparisons. Right? So the trick is to pick 2 new elements. the next element, and the one after next. We know nothing about them. We compare them, and then with one comparison, we know that one of them is a potential min, another one is a potential max. Do you agree? And then we compare potential min with the current min and potential max with current max. So for every new two elements, let's ignore initialization. We need to do 3 comparisons. So roughly speaking, we need 3n over 2. We will do slightly better in a second. All right? Could we do it? You and I? Okay, let's do it. Anybody suggests a name for it? Min-max element, yes, that's what it's called. It's in the new standard. But let us implement it, min-max element. Okay, so start.
And then T.
I don't think it's T.
Oh, so can you iterate this?
By the way, with all this food, could we go up? We didn't finish something. Could we go up? Forward iterator, and we forgot something in the requirements. Guys, we forgot something. Help me, what we forgot with the requirements. I is, of course, a forward iterator. We need to say something else about what? About compare. Right. So what could we say about compare? On a new line. They allow next multiple line. So what would you suggest? Compare is
strict ordering on star.
on. No, this is not quite right, but start with what he says.
Strict weak ordering.
On what?
On the values of
On the value type of forward iterator. Not on forward iterator, but on what, as Arnab says, on whatever star returns. And whatever star returns is known as value type. We will learn eventually how to get value types out of iterators, but not as yet. Right? Why I wanted to put that is because we obviously could use exactly same type requirements for your function, right?
Min-max.
Min-max element. Okay, now. Param wants something.
Should we also say first, last in a valid range or anything like that?
That is, okay, should we say that first and last are valid range? The thing is that if we do, we're going to be saying it in every single algorithm we write from now till the end of eternity. So what do? We say it once in the beginning of whatever, our book or the course or C++ standards, that all the algorithms presuppose that first last is valid range. Somebody, yes?
After you return 2 iterators.
See, he's right. We're returning, it's often the case, I said it's often the case. He's quiet, but then when he opens his mouth, one needs to listen. So, for min and max. Because if we return 1, we'll have a tough choice. Which one? Right? So, yes, guys, I'm not watching. So what do we need to return? You'll get your chance. Everybody will get. So what do we need to do? if we have two things, what do we need to do? First of all, we need to return both. You would agree. How do you return both?
And return a pair.
Yes. So how would you say it? Do you know how to say it?
A pair, I.
Well, it's a little bit not quite like that, because pair could be homogeneous or not. So you have to say pair of I. Because on both first element and the second element, it's the same I. Right? This is just the rule. Because it could be pair of I and int. It's also a pair.
So you compare the first and the last element.
No, this you could never do. First of all, why could you compare last element? Why could?
Last doesn't point to an element of points.
Yeah, because it points past. Guys, again, you have to, let me again explain. This is a frequent mistake. And there are all kinds of explanation why it is the case. The fundamental thing, it's mathematically impossible to describe algorithms on sequence with n elements with n positions. You need n plus 1 position. You just need, it's not because it's C++ or whatever. You have to have n plus 1 things to describe positions in the sequence of n elements. Let's assume you have 4 elements and you want to implement linear search. How many possible things could you return? 5, not 4, 5. Why? Because you could return first, second, third, fourth, and then it's not there. You need to return something which indicates that it's not there. Right? You say, oh, this is just an exception, linear search. No, let's assume we have sequence of 4 elements and we want to partition it in good and bad elements. How many partition points do we have? 5. It could be all of them are good, 3 of them are good, 2 of them are good, 1 of them is good, none of them is good. 5 positions for 4 elements. That is just mathematical necessity. Sequence with n elements requires n positional things to describe algorithms on it. Right? So this has nothing to do with C++. It's just everything to do with structure of the sequence of n elements has n plus 1 interesting positions. Right? So last is this position which does not correspond to anything. It is past the end. It's not found. It's, if you know, do you know Lisp? Nil. Right? This is nil. You couldn't compare nil. You couldn't say car of nil because nil has no car. Even a bicycle it doesn't have. So that was an attempt to joke. But again, what should you start with?
Need to compare for empty range.
Just how do you compare for empty range?
Okay. First is equal to last.
Yes? What would you do?
Return last.
No.
Yeah, it needs to return a pair.
Yes? What kind of pair? With which values?
First and last.
Last and last. Yes. It could be, again, it could be first and first, but Nick convinced us that it should be last, last. Right? Which is the indication. No, it doesn't have any min or max. It doesn't have anything. Okay? So we got the first line. Now, what do we do?
In that line, does it make sense to give first comma last?
What?
Returning first comma last.
Does it? Well, argue with Nick. He says it's last, last. Because he claims, and I think he is correct, that last is the solid indication of not there. Right? And what you say, Min is not here, max is not here, it's just kaput. So I think it's last. But you can, of course, return first last. Okay, but what's the next step?
So I min element equals first.
Mm.
Then I max element equals plus first.
Could you do that? Should you do that?
First plus.
Okay, let's try that. Let's try and see what happens.
Increment it and then
Yes, you want incremented, but it's not even the point, guys. The point is that there are some special cases. You see, like if you have a list of one element, you really don't want to do any comparisons. If you have a list with two elements, sequence, range, whatever, you want to do how many comparisons? One comparison. We need to assure that. So okay, so tell us what to do. Again, you know that I don't like it for an obvious reason. I don't like using plus inside expressions, but that's all right, it works.
so compare min element with the next element.
With which next element? Just tell us the code. If
Compare CMP plus first.
well, first of all, we're probably comparing values, not iterators.
Pointer to plus.
Star.
Yeah, star. Plus.
First. And at that moment, the CPU melts. Do you see why it melts? Because you see, you did this check, which entitles you to do 1 plus plus. But if you do 1 more plus plus, there is a huge chasm there. And at the bottom of the chasm, there are monsters. Yes? You couldn't go. You don't know. You have to always guard your steps with what? What should you guard your steps with?
Check for end conditions.
Check for end condition. How do you check for end condition?
Whether first is
What's the end condition?
or first is last.
Yeah, that's the end condition. That's what you did right here, by the way. You checked for the end condition. You say, I'm already at the end. There's nothing to do, return. So we got that right. Yes?
So after you increment, you need to check whether it's last.
That's always good. After we increment, so which line do you want to do the?
So after you do that, after you do the increment,
Yes.
check if first equals last. So you need to return a pair, which is which one would be max?
Okay. So what do we know at this point? How long is our sequence, guys? 3 guesses. 1. If we have a sequence of 1 element, where is the min? Where is the max?
First one.
So,
What do we return?
Min L, min L.
Yeah, for example. Twice. Min is equal to max. Right? Everybody agrees? Okay. Now, Now, at some point, let me give you a hint. You have to start thinking about, looping. Because unless you get to looping, we will never finish writing the code.
Instead of that expansion.
But you see, another good rule to remember. Okay, could we just, for my benefit, move this plus plus first here, and then do the max out? Yes, thank you. Another good rule: every time you do a comparison, you're done with it. You could go ahead, increment. Yes.
Sure. Yeah.
Yes, thank you. Okay, so what do we do here?
So we can compare first with the
You want to compare first with what? What is our algorithm? Let's go back to the algorithm.
you compare the current element with the next element.
What is the I mean, since you never introduced current, you have to. I mean, current is equal to first, or is it? Is it? That would be. You see. Okay, let me gently sort of give you a few hints. Remember when I described the algorithm in English, I said that first we establish the position of min and position of max. And then what do? We get two elements. Right? But have you, in order sort of to find the first min and first max, what do you need to do? What? Okay, so let me teach you how to write code like that. What you do, you sort of look at all of this, says, oh, this is very nice, but I really don't know what it is. Could we center around here? Around here. So, because I want to put a bunch of empty lines here. Right? So, what you want before you go into the loop, you want to assure that you already have min and max selected somehow. You don't know how. We'll write it later. Do not start writing things from the beginning, because you don't know what's in the beginning. So try to write code from the middle. And the middle is literally, let us write something. No. Let us go here and say somehow we have a loop. So we say while ... Well, it means you have no idea how to stop the loop as yet at this moment. But then let us try to write the body of the loop. Remember, that's where I described the algorithm. Start with where I described the algorithm. Write this. Then go back and make the invariance on which we depend be true. Do you understand what I'm saying? So we get to while, we say there's some condition. So let us write // here. So what do we know? We know that min element points to the current minimum. Right? We know that max element points to the current maximum. And somehow, what else do we know? That there are two more elements available. Somehow. And what would we call them? I would suggest that at this point we'll have first and next. because, so, you know, first we will be moving along and next. And we haven't touched them, so somehow by that point, first moved past the elements we examined, yes? Do you see what I'm saying? Okay, so let us write from this point on. So we have max element, min element pointing to current things, and we have first and next somehow pointing to the next two unexamined elements. Everybody? You have to say words now. I could dictate the code, but that wouldn't be interesting. Oh, maybe for you it would be. But try. Let me make it even simpler. Even simpler. Let us say that what we do, I will, again, when in doubt, introduce extra variables. You could get rid of them, but they will help you thinking. Right? So why don't we call, you have potential min and potential max, but we actually don't know whether a potential min and potential max as yet. Right? So we'll say the first guy is potential min, the second guy is potential max.
So high potential min equals first.
Yes?
Potential max equals next.
Yes? Good. Now, but it's not really true. Make it true.
So we need to compare potential min and potential max.
Yes.
So if compare start potential min comma potential start potential max.
I would do it a little bit differently. Again, I would say that you're right unless you're really wrong. That is, min, if they're equal, do you need to change them? No, they're exactly right. Remember, we're putting min, we prefer min here, max there. So I would say that only if potential max is less than potential min. Do you agree? Okay. What would do if it happens?
Happens in the swap.
Exactly right. What do we do?
Potential start potential.
Potential, yes? Not star. We swap pointers, not values. Everybody follows us here? And what do we do after that? So we have current and potential. What do we need to do?
To compare min and max. Current min and max.
Current min, no, we never compare current min and max. Well, we did compare current min and max. Now we need to compare potential with current. This is true. We know that this points to current minimum. So we don't need to that somehow we guaranteed already. Yes?
So
If compare
potential max,
yes,
max element,
Yes, you do need stars. Again, remember, dereferencing does not happen automatically. You have to say when it's done. Yes? Okay, let us think about it. When does this potential replaces max?
So it should be the other way around. It should be compared star max element, star potential max.
Why?
Because that max element is the one which we are returning, which should be the maximum of the list.
Yes, it should be the maximum of the list. But which way, again, remember we have this additional, you see, things are getting tricky now. We have to think, when they're equal, do we replace them or not? For max, yes. For min, no. So there should be some asymmetry. Okay, so what we need to do if this is strictly winning, no, if it's strictly, if it's non-strictly winning, if it's greater or equal. So how do we do greater or equal? We need to use not someplace. If not compare, yes, potential max, yes. What do we do now?
Swap. We can swap.
Do we need to swap? We don't need to swap.
Just put the value of equal to.
Just change the max element. You don't care about, saving the old value of max element. It's of no concern of ours anymore. It was, mistaken value. Do you agree? So what do we say?
Max element equals potential max.
Very good. And we need a couple of more lines. We need to do the same for, yes, but a little differently. Okay, tell us.
So if compare,
Michael probably hates me because I move all the time. If compare
min element to potential min,
min element, yes. But you are always forgetting something. Star.
star potential min,
Yes. Yes. Close paren, I'll help you.
close bracket, open. So min element,
Yeah.
potential min.
So, guys, that's the core of the algorithm. Oh, that's correct.
No, the order of comparison is wrong.
Oh, no. This is, sorry, I wasn't watching. Yes. So if the guy who is coming is less than the current minimum, only then you replace. Yes. Sorry. That's why I need to retire, guys. Okay, min element, all right? So that's the core. Right? So there is this great principle I have been teaching people for years. Start from the inside. Figure out what's the core of the algorithm, because that's the core. Right? And now what we need to do is to figure out that it all works. So we need to assure that when we enter the loop, it all works. Then we actually could sort of figure out whether we do need first and next, you know, and all of this. And then we need to figure out another little thing. What's the other little thing? One element at the end. You see, we go by twos, but you know, in 50% chance that there will be no two elements at the end. There'll be only one remaining element. So what do we need to do then?
We need to check if we
Yes. We need to check against both min and max. Right? Nothing else could we do? Right? So we need, again, this is a typical thing. This is the main loop. Right now we are in dreadful situation. Could we? They don't do exercises. I don't want to drag. Do you guys promise to finish it at home? No, I'm honest. You have to finish, and you have to test. All of you. We're almost done. I have the finished code, but that wouldn't be interesting if I just asked. Ryan could post the finished code in like 30 seconds, but it's not interesting. I beg you to finish. You know, I'm out of time. Because that would, I could finish it in the beginning of the next class, but I have this very exciting algorithm, which again, let me tell you what we will be doing. After you finish this, the next problem, and the problem which I recommend that you think about, is the problem of finding min and second min, smallest and the second smallest. And of course, with smallest possible number of comparisons. That's the tricky thing. And preferably with using very little extra storage. You know, we have to make things tough. So try to think about it. It's not as simple. I'll tell you the story next time. But please finish this. And this, if you want the paper by Ira Pohl is easily findable on the web, and he proves that this algorithm is optimal. That is, you cannot find min and max better than by doing this. Right? So this is an optimal algorithm, and it's also practically good. We don't have time right now, and I don't want to waste time, but I have a witness here that when you time it, it is actually considerably faster, say 30% faster in practical cases than first finding min and finding max. So it does actually work. And it also will be in the new library, which you will get whenever we'll switch to C++11, because the algorithm is in the new standard. And it's called, any guesses? Min-max element, yes. All right, so see you in a week.